So what I want to do then today is to just finish off these integration techniques. There are 4 of them that we use. Algebraic substitution that we've looked at. Trigonometric substitution that we've looked at, that's what we were looking at last week. Using partial fractions, which is the first thing we did this year. And then today I want to look at integration by parts. The exam, when it comes, that's going to involve using some standard results. So you know last week we were talking about getting our integral to look like the standard results and then using them. So you get the opportunity to use some of these standard results. And those sorts of questions will be towards a pass and a good pass. If you want to show how these are arrived at, which is showing more understanding, then that's towards the merit and distinction. And there's a handout that I'm going to give out to you on finding the volume of a storage tank which uses integration by one of these methods. So that's a nice practical example to have a look at. So I will hand that out. So standard results, what do I mean by that? Well, here are a few, and you remember those from last week. We looked at 1 or 2 standard results. So if I want to integrate something like this, what I'm doing is I'm trying to get the problem I'm trying to solve to look like that standard result. And that sometimes is not easy, and that's probably the hard part of using these things. Once I've got it to look like a standard result, then as soon as it looks like this, A is going to be this number here, and so long as that's x, whatever x is, that will be this value here. So it's the angle whose sine is x over a plus c. And as I was saying last time, if you want to see how this standard result is arrived at, then have a look in the textbook. Here's 2 more standard results. And for those distinction type questions, you might be asked to maybe try and have a go at seeing how one of these is arrived at. And if you have a look at it, actually, it might look a bit awkward to start off with, but once you've got the idea of how they work, it's not too bad. So those are the sorts of standard results you get in the exam, as well as lots of other integrals. We looked at evaluating something like this. Here's an example of one where we want to use a standard result. And the standard result we're going to try and use is this first one we had here. Sorry, the second one, this one. So x, what's x? Well, if we look at this, in fact, it's not x squared, it's 4x squared. So what we have to do is think about making this something squared. So we let 2x be inside a bracket. If I square that bracket, I'll end up with 4x squared, which is this. So what I do is I call that this. So I can say I've got something squared. And then I let u equal 2x. So that we've got the integral between 1 and 0 of the square root of 9 minus u squared. But we're still integrating with respect to x. We need to be integrating with respect to u. So can you remember what we might do next? What would be a good plan? The sort of thing we've been doing before. Sorry? No. I've got to change this. This has got to be du to be able to do the integral. So what do you remember what we do to change this? Is this a substitution idea? Right, we differentiate this. Good. We find out what du by dx is and then change it. So we have that. Du by dx equals 2. So dx equals du over 2, this idea of algebraic substitution that we've looked at before. So now the integral becomes the integral between 1 and 0 of the root of 9 minus u squared times du over 2. The 2 can come outside the integral. And so now we've got half integral between 1 and 0 of the square root of 9 minus u squared with respect to u. And this is a standard result, which is this one here. So a squared equals 9. If we look at this example, a squared equals 9. So a equals the square root of 9, which is 3. So we know that a equals 3 and u equals 2x. So then we can put in the substitute. We can use this standard result where a equals 3 a u over 2 root 9 minus u squared, and then we remember that u equals 2x. So finally we get this, and then we can put the limits in, finish it off. Okay, so it's that sort of idea of getting our integral to look like a standard result, and that's what I mean by that. The standard result is just x squared. We've got 4x squared. So what do we do about that? We make sure we've got something squared, and that will now be our x. So we call that u, and away we go. We looked at the beginning of the year of integrating using partial fractions, so just this video will be here to look at, and we've looked at lots before. Remember what we do? The preamble for this is, the whole point is about a standard integral, and do you remember we talked about this? The integral of 1 over x is log x. So to integrate this, we're going to try and get it look like a fraction of something over x. And so what we do is we split this thing into partial fractions. Do you remember using the standard result? If instead of having x we've got 3 plus x, we let u equal 3 plus x. In other words, we use algebraic substitution, so we can then use the standard result, so we end up with log of 3 plus x plus c. So this idea is used in doing this partial fractions problem. So what we do is we split this into something over x plus 3 plus something over x minus 1 plus something over x minus 1 squared. Using the idea, if I've got x minus 1 squared, I'll have some term involving x minus 1 and some term involving x minus 1 squared. And there are examples of this in the text. So we split it like this. And then it's all about, the partial fractions idea is all about finding a, b, and c. So we find the common denominator, we multiply x plus 3 by x minus 1 squared to get the same denominator, both sides, and so on. So then we equate numerators. If you remember the technique, I don't want to run through the whole thing now because we've spent quite a lot of time on it. We equate numerators, let x equal a value, so some of it disappears if you remember. So we can find a, b, and c eventually. So once we've got a, b, and c, we can then put them back in. So all this is about finding a, b, and c. The idea of letting x equal value so some disappears, or setting up simultaneous equations. So we end up with the integral that we started off with being the same as the integral of 2 over x plus 3 plus 3 over x minus 1 minus 4 over x minus 1 squared, and then we can use the standard integral to do it. So the working is here, and you can take your time and have a look through it and make sure you understand it. So there's integration using trigonometric substitution that we were looking at last week, integration using algebraic substitution, and partial fractions. What I want to do today is looking at problems like this, where we have to use integration by parts, which is this formula here. So we might want to take notes from this point. So this is something that we did look at last year, okay, briefly. So let's review this technique. If you remember, the idea is to call one bit u and the other bit dv. In here we've got two parts, 5x times e to the 4x. So just like the product rule, in fact this method comes from the product rule, we have x appearing twice, so we know we've got two functions involving x multiplied together. So that's an example where we're going to try and use the product rule. The integration by parts rule. Instead of it one bit equaling u, though, we're going to let one bit equal u and the other bit equal dv. So rather than u and v, we'll let one bit equal u, and we're going to differentiate that bit to get du, and then we let the other bit equal dv, so we're going to integrate that and get v. That's the method. And you remember that the point of it is let the bit we're going to equal u be such that when I differentiate it, the x disappears. That's how it works. If I differentiate, if I let u equal 5x, and then I differentiate it to put that in here to get du, then I won't have an x term anymore, and so I should be able to do the integral, the standard integral, hopefully. It gets complex when I've got, say, 5x squared here. Then I'd have to use it once to get rid of the 5x squared to become 10x, and then I'd use it again to get rid of the x. So sometimes you have to use this integration by parts method a couple of times, 2 or 3 times, to get rid of one of the terms. That's the way it works, by getting rid of one of the terms. So what we do is we let u equal 5x and we let dv equal the other term, which is e to the 4x. So then, as we've let u equal 5x, we differentiate that to get du by dx equals 5. That's good, because now the x term has disappeared. And if dv equals e to the 4x, then v equals the integral of e to the 4x, which is, you know what you do? The 4 comes out and goes underneath. Okay, quarter e to the 4x. So now we've got our two values. Yep. So now we've got the rule, integral of u dv equals uv minus the integral of v du. So the integral of u dv is our integral. In other words, I've let u equal 5x and dv equal e to the 4x. So I can say the integral of 5x times e to the 4x, which is what we're after, now becomes u, which is, aren't they? Yes, I am. Yeah. U, which is 5x, times v, which is 1 over 4 e to the 4x, minus the integral of v, which is 1 over 4 e to the 4x, times du, which is just 5 with respect to x. So now I end up with an integral that's doable, because x only appears in it once. So this equals, tidying up, 5x times a quarter becomes 5 over 4 x e to the 4x, minus, I can bring the 5 and the 4 outside the integral, e to the 4x dx. And so we've just got to integrate this again. It becomes 1 over 4 e to the 4x, doesn't it? So this equals 5 over 4 x times e to the 4x minus 5 over 4 times the integral is 1 over 4 e to the 4x. Yeah. And at the end, plus 6. I've left it like that because we can see now that the 5 over 4 can come outside the bracket, and so can e to 4x. So I can take 5 over 4 e to the 4x outside a bracket, leaving inside the bracket x minus a quarter plus c. That's all we're left with, isn't it? Yeah. So now, of course, remember, this is actually a definite integral, so we don't need the c. We've got to put our limits in of 0 and 1. So I've got to let x equal 1, work out what it is, and then let x equal 0 and work out what it is. So I'll leave you to finish that off and see if you can get the answer in the text, which is 51.5, yeah.